What's the direction of the force on this ball? Pointing towards Q1, right? It's attractive because they're opposite charges. So we know that's sort of going in. So the force is really pointing in this direction. So I'll say there's your Fe. I want to know what that Fe is. Well, the way you calculate the magnitude of electric force, and this kind of makes sense, it all depends on charge, right? So the more charges you have, the more charge this has, the stronger it's going to interact with that. The more charge Q2 has, the stronger it's going to interact with whatever this charge is. So it turns out that when you calculate electric force, you look at the product of the charges involved, just like gravity, very similar to gravitational force. And because the interaction happens at a certain distance, it's inversely related to the distance of separation. Right? The further apart they get, the weaker their interaction. And it turns out that it's actually related to the square of the separation distance. So every time you double the distance, the interaction decreases by a quarter of its original value, or is a quarter of its original value. So it goes down pretty quickly, inverse square of the separation distance. Now, I got coulombs, and I got meters squared. Something tells me that doesn't come out to newtons. So we got to do something to fudge it and put in our engineering factor. Normally I call it the crap factor or the fudge factor, but we'll call it the engineering factor. So we're amongst engineers, we're among friends. Right? So we'll call it the engineering factor. So there's some constant in here that when I multiply by the interacting charges and divide by the square of the separation distance, magic gives us units of force in newtons. Okay, so what goes in here? Well, what must the units be of this thing? What would they need to be to get units of newtons out? And I'm going to make you think on the first day. This better have units of newtons in the numerator, right? And it better have meters squared in the numerator, so that they'll divide out these meters squared. And it better have coulomb squared in the denominator to get rid of the darn coulomb units. So whatever the unit is, it looks something like this. Okay. So first thing I'm going to do, I know what the units are going to be. I'm going to call this thing K for now. We'll make it better than K, but for right now I'm just going to call it K. Sometimes we call this number Coulomb's law, or Coulomb's constant. If you look in the front of the book, you'll never see this number. But for now, we'll call it Coulomb's constant, because we have another way of expressing it. It turns out that K, again, part of the problem with K, how many Ks have we seen now? The Boltzmann constant, the elastic constant, sometimes we use e to the minus kt for an exponent.
It's like 26
it's
letters.
everywhere.
I keep using this.
So we'll figure a better way to deal with this. But for now, let's just point out that this number isn't an easy one to remember. It's 9 times 10 to the 9th.
9 times 10
Or
to the
8.99 to be a little
That's
bit more
better.
proper. But for all practical purposes, for any calculation, it's about 9 times 10 to the 9th. And the units of this thing better express newtons, meters squared, or coulomb squared. So this is the fudge of the engineering factor that you use to relate force to charge and distance of separation. Now we know the number, now we can do some calculations. So what is the magnitude of this factor? That's plug and chug. At this point, we could say that Fe, we've got our 8.99, that's 10 to the 9th, Newton meters squared. I'm not giving myself enough room. Coulomb squared. And then we've got, over here, we've got 1 coulomb. I got to keep track of my charge. Is it positive or negative? I'm going to remind you. I'm going to tell you now, but I'll probably remind you a few times later. use the negative, or use the sign of the charge with the value, and you'll see why. So it's minus, or plus 1 coulomb times minus 2 coulombs. Oh, I hate when I run out of boards. They have it on the wall. They don't like it, they can give me more dry marker space. I grumble about it every year. And then we divide this by the separation distance of 5 meters. Ah, squared should be outside, not inside. You see, I get to talking and writing and I forget what I'm doing. So, for all practical purposes, and this ought to be shocking. Oh, well, maybe not. If you plug this stuff into this equation, it's basically 8 times this number, right? Or, yeah, 0.5, 0.25, the inverse, it's 4, 4 times 2, 8, 8 times 9, 36 times 10 to the 9, so 3.6 times 10 to the 10th. 10 to the 10th newtons. We can fudge with that a little bit, 3.6, 3.5, whatever, but it's about 3.6 times 10 to the 10th newtons. Okay, crazy number. Why? Because we're talking about, as the old phrase goes, a spit load of extra electrons somehow, right? So we got stuff, but look how big this is. We're only talking, well, okay, I didn't draw it to scale. This distance apart, 2 charge systems, and we're talking the amount of force that you could probably hold a building up with. Moral of the story? Coulomb quantities of charge are hellaciously large. They're like moles of atoms. They're large quantity. The SI basic unit of charge is tiny for a reason, because each of these electrons interacts with such strength with other fundamental charges, it doesn't even compare to gravity. It's off the chart. You know what happens when things are off the chart? You create string theory and add another 100 dimensions to try to account for all of these orders of magnitude that don't fit, damn it. That's what you have to do. Now, the second part, I know we got to go here. That's the magnitude, but we got to describe the direction. I left a minus sign out for a reason. Okay? Kind of cheating.
Yeah.
I'm going to put the minus sign here.
Okay.
Because I told you, don't lose that minus sign.
Right. Okay.
But here's the problem. What does a negative magnitude of a quantity mean? Direction. Direction of what? Doesn't direction depend on how you define it?
Yeah.
So you have to take your pick. Right? So
Right.
you got to be careful. So to establish direction, I should have did this first, but I intentionally wanted to be deceptive. When you calculate this expression, the direction of this force is radial, or along the line of action between the 2 charges that are interacting. Radial is the wrong choice of word.
Okay.
It's along the line of action. But here's the thing. If I'm calculating the force on Q2, the origin is on Q1. And the positive direction is from Q1 to Q2.
Okay.
Okay? So if I were to rewrite this in a useful sense, I would say,
Positive.
according to this expression, my coordinate system has at least one direction, the R direction, if you will, axis, whatever, pointing from Q1 to Q2. I'm going to put my little R in here now. And it's negative, meaning that if positive is from here to there, negative is pointing in the opposite direction. So when you have attractive interactions, by definition, it's a negative force vector. Kind of like gravity, right? We always call up positive, so gravity's pulling down negative, attractive, negative. Now, I never really gave you a reason why, other than things that are up are positive and things that are down are going to be negative, right? There's kind of a motivation for that. So, please read chapter 21 when we come back on Thursday, I want to look at this on a microscopic scale and sort of correlate it now to the interactions, say, between electrons and protons. Numbers start getting less friendly, let's say. But there's a lot to be appreciated in the concept.